be discussing the single source shortest paths problem, which you have probably seen in your previous courses, but our objective is to understand it as deeply as we understand DFS and BFS now. Okay, so we are interested in understanding this deeply, so I'm going to draw the example first. So this is an example from the book, from Cormen's book, I believe. Ten, 5, 1, 2, 3, 9. One more. This is 7. Okay, so this is a weighted directed graph, and here we are given a source. And the problem is to find for every vertex in the graph the shortest path from the source to that vertex. So we need to find the shortest path from A to B, from A to C, from A to E, and from A to D. So that's why this is called the single source shortest path problem. So there are multiple paths here, but there is a single source. Okay, so any questions on the problem? Now the path that we are looking for here is the weighted path, or the distance that we are using to the distance here is the weighted distance that we are using to compare the different paths. So we are interested here in the weighted distance. And the weighted distance is just the sum of edge labels along a path. So for example, the weighted distance for the path A, B, C is 11. You sum the weights of the edges along that path. Now, if we had been interested in the unweighted distance, we have already studied an algorithm that solves this problem when we are interested in the unweighted distance. And what's that algorithm? BFS, yeah. So if we are interested in the unweighted distance, then we can use BFS. It will give us the unweighted distance. The unweighted distance will be interesting if all edge weights are the same. They are all the same, whether they are 1 or not, or anything else. As long as they are the same, you can do an unweighted distance. They all have the same weight, and you can do BFS. So clearly, the algorithm that will solve the weighted distance problem has to solve a more general problem. So it's expected to be an algorithm that takes more computation. So the asymptotic complexity of Dijkstra's algorithm, based on the problem description, is expected to be greater than the asymptotic complexity of BFS. Okay. Now, what's the main idea behind Dijkstra's algorithm? Well, Dijkstra's algorithm is based on, first of all, we have the source. We look at the neighbors of the source. Well, first we just label all vertices with the distance of infinity. We haven't discovered anything yet. So first we look at the neighbors of the source, And among the neighbors of the source, we'll observe that there is a path, or the weight of the edge from A to E is 5, and the weight of the edge from A to B is 10. From this, we know for sure that this path, or this direct path, or this one edge path, is the shortest path from A to E. Right? We know that we cannot, it will be impossible to find a shorter path from A to E. But it may be possible to find a shorter path from A to B. Right? So generally speaking, if this is your source, and then you have a bunch of neighbors with with distances like 3, 4, 5, 6, 7. So if these are the distances that you have, then I know that this path is the shortest path to vertex A. But I don't know if these are the shortest paths to the other vertices, like B, C, D, E. So this is the only one that I know that this is the shortest path, and it can't be any better than this. Okay? Why?
Because if you're going to that particular node through a different path, that higher cost would be added. For example, if you want to go to A through B, then we'll have to add the cost of S to B and then B to A.
Exactly. Yeah, exactly. So if assuming that there is another path, from source to A, that other path will have to go through one of the other vertices. And, well, it will have to go through either B or C or D. But obviously, we cannot get anything better than 3 because the distances for these, or the edge weights for these, are greater than 3. So any path that will take us from S to A through any of these vertices will have to have a length that is, at least 4, in fact. In this case, at least 4. Right? Now, this argument is based on the assumption that edge weights are positive. So in this argument, I'm assuming that edge weights are positive. Otherwise, if negative edge weights were allowed, then there can be a better path from S to A that goes through C, for example. I could have had something like this with an edge weight of -4. Right? So in this case, with negative edge weights, a shorter path from S to A is the path that goes through C, and the total weighted distance for that path will be what? 1. 5 minus 4 is 1, and 1 will beat 3, is better than 3. So what does it mean? This means that Dijkstra's algorithm is a valid algorithm for solving the single source shortest paths problem only if edge weights are non-negative. If you have negative edge weights, then Dijkstra's algorithm may fail. Okay, and this is just a simple example that shows that it fails, in fact, on this simple example. So you can use Dijkstra only if you do not have negative edge weights. If you have negative edge weights, we will study another algorithm for solving this problem. Okay, but in fact, when you have these distances, this does not only apply to the neighbors of the source. The same argument applies to any vertex or to any set of vertices. If at any time in the algorithm, if you have, so let's draw another picture. At any point in your algorithm, you'll have your source, and then you will have certain paths to, this is vertex, let's call it A1, vertex A2, vertex A3, and let's call this AK, and suppose that these have some, let's put some numbers first and then we'll put symbols. Assuming that this has a distance, a computed distance of 5, and this has a distance of 7, 8, and this is let's just give them some numbers, and A4 has a distance of infinity, and everything else has infinity. Okay, so at any point during the algorithm, some of the vertices will have been reached, some of the vertices have not been reached yet. Okay, so for example, in the beginning here, I have a distance of 10 for B, and I have a distance of 5 for E, and all other distances are infinity. Of course, at the end of the algorithm, every vertex, every reachable vertex will have a non-infinite or a finite distance. But in the middle of the algorithm, you will have, vertices will have distances, and some of the vertices have not been reached yet, so they will have infinity. Now, if I have a vertex with a distance of 5, I am certain, assuming that the edge weights are non-negative, I am certain that this is the shortest path to A1, that the path that I have discovered is necessarily the shortest path to A1. But for all other vertices that have distances greater than the minimum, I'm not sure that if this is the minimum or not, because I may have a path to A1 to this should be A2. I may later on discover a path from S to A2 that goes through A1, right? And it has a weight of 1. Then this is 6, and 6 beats 7. So for any other vertex, there is a possibility, to discover a better path. But for this vertex that already has the minimum distance, the possibility is not there. It will be impossible to find a better distance or a better path, because that better path will have to come through one of the other vertices. And if it comes through one of the other vertices, you'll have to pay at least this cost, or this cost, or this cost. So the vertex that has the minimum distance, I'm sure that it already has the minimum distance from the source.
How do you know that it has the minimum distance? I mean, because we have the unknowns down there.
Mm-hmm. Oh, okay. So you are asking, what could these have something like 4?
Yeah.
Well, that's a good question. Could this have a 4, or this could be a 3? Will this be possible? Why or why not?
Because there might be cost from A5 to A1. That might be more.
Well, that might, but I'm not looking for might. I'm looking for why will it be impossible for this to have a distance of 4, or a distance that is less than 5? Why will it be impossible?
We're sorting? Because we're sorting?
No, it's these are just a bunch of distances. Well, it's because in order for this to have a path, that path will not come from nowhere. It will have to go through one of these vertices. Why? Because, first of all, A4 is not a neighbor of S. Is not one of the neighbors of S. Why? Because if it had been a neighbor of S, it would have had a finite distance already, right? The fact that it has infinity implies that it's not a neighbor of S. If it had been a neighbor of S, it would have had a finite distance already, and that distance would have been the edge that connects S to A4. So we know that at this point, if we have some finite distances and infinite distances, these guys are not neighbors of the S. But if they are not neighbors of the S, any path that will connect S to them will have to go through the vertices that have finite distances. But the vertices that have finite distances have these distances already, so it will be impossible to find something that is better than 5, because you'll have to go through one of these. Okay? Clear? So this is basically the the meat of the proof of correctness of Dijkstra's algorithm. So this is the main point, and that's why, in fact, selecting the vertex with the minimum distance is a greedy choice. So Dijkstra's algorithm is a greedy algorithm, and this argument that I was just describing is an argument that proves the greedy choice for Dijkstra's algorithm. It's a greedy algorithm. Always the vertex with the minimum distance, we know that this cannot get any better. Everything else can get better, but this cannot get any better. Questions on this? Okay. Now, given this argument, so now we know at this point that E cannot get any better, but B may get better, and in fact it will get better. So what we will do is the following. So we will put the vertices in a data structure that we will describe later, what that data structure is. So we will put the vertices A, B, C, D, E, F, and for each vertex we're going to put the distance, the D, and we're also going to put the parent. Why the parent? Because we would like to track the actual paths, not only the distances. So this is the parent. So initially, the source A will have a distance of 0, and everything will have a distance of infinity. And the parent is going to be null for everything.
There's no F.
So there's no F.
Oh, there is no F? Okay. That makes it easier. Okay, so first step, look at the neighbors of the source. I know that E has its minimum distance, so I'm going to update the distance of E to 5, and I'm going to update the parent of E to A, and I'm going to update the distance of B to 10, and this I'm going to update it to A. Now, once I do these updates, A is done. Now, I know that E cannot get any better than this. So I will take it first, I will update the neighbors, and then I will take it out. So I will update the neighbors of E. What are the neighbors of E? The neighbors of E are B, B and C and D. So for B, now I will update the distance of B, because now I have discovered a better path from source to B. And this distance now, the 10 will get updated to what? 7. Yeah, because 5 plus 2. So this is going to be a 7. So now this is 7, and this is, now the parent is E. So now I have discovered a new path to B that comes from E. So it doesn't come directly. So the parent is the immediate predecessor of that vertex in the path. So the vertex that precedes this vertex in the path. That's the definition of the parent. So now the parent of B now is E. It's no longer A. Now for C, I will update the distance to what's 5? No, 5 plus 9. 5 plus 9, which is 14. And for D, I will update the distance to 7. So for C, I have 14. And the parent is E. You can get rid of this. And for D, the distance is 7, and the parent is E. Okay? Now, I'm done with E. Now, at this point, which vertex I know has its minimum distance? I think, I think I got these wrong. I think this should be, so this should be the 3 and this should be the 2. I got these switched. So, so 3. So this is going to be 8, not 7. I just discovered this. So this is 8 to B, and this is 8, not 7. Okay. So now I'm done with E. I found the shortest path to E. A is the source. Among the 3 that are remaining, which one of them I know has its best distance that will not get any better? D. So I know that this will not get any better. So now I know that this is the best. So before I take it out, I'm going to check on the neighbors to see if I can discover better paths to these neighbors. So what are the neighbors of D? First neighbor is C. And C, now I can update this to 7 plus 6, which is 13. So C is now 13, and it now has a new parent, which is D. Now when I look at A is already out. It's already done. So I don't update anything. Okay? So now I have updated the neighbors of D. Now I'm left with B and C. Which one of them I know that this is the best distance for it, and it will be impossible for it to get any better? B. So it will be impossible for this to get any better. So this is the best distance to B. Now I will use it to update the neighbors. The neighbors are E, which is done, and C, which is not done yet, but I have just discovered an even better path to C, and that has a distance of 9. So C has now 9, and the new parent is B. So I keep discovering better and better paths. But the point is, at any point in time, the vertex that has the shortest distance, I know that this is not going to improve. And this will always be the case as long as edge weights are non-negative. Okay? So now now I'm done with B, in fact. And I am left with C. And C will be the last vertex, so it's not going to update anything. And it will have a minimum distance of 9. And the path, what's the best path now, the shortest path to C? I just trace the parents, trace them back. So parent of C is B. So this is the edge. Then I look at the parent of B. What's the parent of B? The parent of B is E. So this is another edge. And what's the parent of E? The parent of E is A. So this is the path. So you find the path, the actual path, by tracing the parents back. Okay? Any questions? So I think we are now ready to write the code. So for Dijkstra's algorithm, we're given a graph and a source. So the first step, we just initialize all distances to infinity for each vertex u in G, u dot d equals infinity, and u dot pi equals null. This is the initialization. Then I set the distance of the source, s dot d, to 0. Then I have to put these vertices in some data structure. Now, what would be the data structure that will give us just what we need here? What's the data structure, the right data structure for
Stack.
stack? Do we always take out the latest vertex that we push? No, in fact, in the very beginning, we put all the vertices, and we always take out the vertex that has the minimum distance, right? The vertex that is done is the vertex that has the minimum distance.
3.
3.
Minimum.
Okay, so a BST, binary search tree.
Yeah, minimum.
Okay, that can work. That may work. That's a good guess. But there is a simpler data structure that is designed just for that.
Can take priority queues.
Yeah, exactly. So the priority queue is designed just for that, just for each time extracting the element that has the minimum value. In fact, that's all what we need. So we insert the vertices in the beginning, and we always extract the vertex that has the minimum value. The vertex that is done, that we know that this has its best distance and things are not going to get any better. Okay, so it's a priority queue. But the priority queue can be implemented in different ways. So we will look into this when we get to the analysis. But let's now just say priority queue. Create a priority queue. Then for each vertex u in G, do q dot insert of u. So we insert all the vertices in the priority queue, and when we extract, we always extract the vertex that has the minimum distance, okay, because we know that it's done and its distance will never improve. It's impossible for that distance to improve. Okay, so then we'll have a loop while q is not empty. We extract one vertex at a time. So we do u equals q dot extract minimum. Then what? So we take the vertex with the minimum distance, we extract it from the queue, and what do we do with it? Yeah, look at the neighbors, exactly. So now we know that it has the minimum distance, so now we do that famous loop that goes through the neighbors that we have been doing in all algorithms so far. So for each neighbor, v of u Now, what do we do here? For each neighbor, what were we doing? We update the distance of the neighbor, but of course we update it only if it's better than the current distance, right? So we compare the current distance of the neighbor, which is v dot d. This is the current distance of the neighbor, with the new distance, which is what? What's the new distance?
U dot D.
U dot d plus the weight of the edge uv. So this is current, this is new. And if this is better, if this is less, we update. So we do if u dot d u dot d plus w of u and v is less than v dot d, then we update v dot d equals u dot d plus w of u and v. Okay, so this is the key step here, the most interesting step in the algorithm. We look at the neighbors. So for example, when we looked at the neighbors of B here, so B dot D was 8, and W of B and C was 1, and C dot D was 13. So the distance of C was 13. So in fact, let's write it U and V. So this was the U, this was the V, and that was the W of U and V. So the distance of the U is 8, the distance of the V is 13, but the distance of the U plus the weight of UV, which is this, is 1. So we updated this to 9. Okay? So this is Dijkstra's algorithm.
We need to update the parent as well.
We need to update the parent?
No, because
Oh, you mean the pi. Okay, yes. So pi.
v dot pi.
Yeah, so then in this case we can say v dot pi equals u. Yes. Now, what's the running time of the algorithm? Now we have to be careful because the operations here, we're using a priority queue, and the priority queue operations are not constant time operations. Okay, in fact, they depend on the implementation of the priority queue. So we have here on this line we have inserts. So how many inserts will we be doing? V inserts. V inserts. And how many extractions? How many times will each vertex get extracted? Once. So then we have V extracts. Now there is a hidden priority queue operation here. What's the hidden priority queue operation here? What's the hidden operation here?
We are building the
Pointing it to the minimum one.
Well, so we are keeping these vertices in a priority queue, and here we are updating the distance, and the elements are ordered by that distance. So that distance is the key in the priority queue. So here we are updating the key, and when you update the key, there will be some, or there may be some operations that will have to be done to add readjust the priority queue. So this is, but how many of these operations will we have? How many of them? How many times will this line get executed? So this is something that we should be familiar with by now. So this line will be executed E times. So this is the famous loop that goes through the neighbors. So in aggregate, this will get executed E times. In fact, the if statement will get executed E times, but the update will happen less than or equal to E. So the update is going to be, these updates here is going to be O of E times the decrease key time. Decrease key time. Now, what's the decrease key time? It depends on the implementation of the priority queue. Now, what's the most popular implementation of a priority queue? What's the?
Well, if it's sorting, isn't that going to be in log n?
Well, what's the implementation of the priority queue? What's the actual implementation? What data structure is used to implement a priority? So a priority queue is an abstract data structure that can have multiple concrete implementations. And the most popular concrete implementation of a priority queue is? No, it's the heap. So the heap is the most common implementation of a priority queue. So if you have a heap priority queue, then you can do insert in what will be the time for the insertion for the heap. So in fact, the heap will do all the operations, all the main operations, the insert, the extract minimum, and the decrease key in what time? What will be the running time? So it will be log n for the heap. The heap can do each of these operations in O of log n. Okay. But the heap is not the only implementation of a priority queue. One simple but useful implementation of a priority queue that can be useful in some cases here, as we will see, is the unsorted array. Now, if we implement the priority queue as simply an unsorted array, how much time will it take to insert an element? It's an unsorted array, so you can put it anywhere. So it's O of 1. But how much time will it take to extract the minimum if it's unsorted?
Log n.
No, not log n. It's an unsorted array, so it's going to be O of n. Now, how much time will it take to do a decrease key in an unsorted array? So what does decrease key mean? It means adjust the elements in the priority queue if the priority queue is ordered in a certain way. But the unsorted array is not ordered in a certain way. So you just do nothing. So here, decrease key in an unsorted array, because you are not adjusting, no adjustment is needed, because the elements in an unsorted array are not placed in any particular order. So this is just 0. Or you can think of it as O of 1. 0 time. Okay, so now if you have heap, all of the operations will be log n. If you have an unsorted array, this will be an expensive operation because it's unsorted. Whenever you need to extract the minimum, you have to search through the array and get the minimum. For insert and decrease key, basically you do nothing. Insert, you just put the element anywhere. Decrease key, you just do nothing. Okay. Now, what's the total running time of the algorithm with each of these data structures? Now, with a heap, the running time of Dijkstra is going to be T of V and E, time as a function of the number of vertices and the number of edges. This is going to be what? V inserts. So it's going to be O of V. Now, what's N here in the heap? Now, N, is it V or E? V, because what we are storing in the heap is vertices, not edges. Okay, so this is going to be O of V log V. This is for the inserts, V log V. For the extract minimum, again, it's going to be O of V log V. For the decrease key, it's going to be O of E log V. Okay, so this is the insert, this is the extract minimum, this is the decrease key. And what's the total? The total is going to be O of V log V plus O of E log V. And in fact, if the graph is connected, what will be the relation between V and E?
Same. No.
V will be at least of the same order. E will be at least of the same order as V. If the graph is connected, you will need at least one edge for each vertex. All right? So E and V will be of the same order. In fact, you know, the minimum number of edges that is needed to connect V vertices is V minus 1, which is the tree. So the minimum number of edges that you need to connect V vertices is V minus 1 edges, and that can be done by a tree. The tree uses the minimum number of edges to connect a given set of vertices. Okay, so in this case, if E equals omega of V connected graph, then T of V and E equals O of E log V.